Okay, in the first part, part A, we're using momentum conservation. So initially you have MAVA, and B is at rest. That's equal to MAVA prime, final speed of A, plus MBVB prime, final speed of B. And so
Here's a clean and professionally formatted
MBVB
presentation
prime
of the calculation
is
shown in the
equal
image.
to MA times VA minus VA prime.
Application of
Now
the
we
work
know
energy
that for
theorem,
elastic
wet. From
collisions,
the work energy theorem, the force
VA
F is given
minus
by
VB
F
is
equals
equal to
frac
negative
times KE,
VA
where
prime minus
KE equals kinetic
VB prime.
energy, S was
This
stopping
implies that
distance.
VA
Then
prime
given for object A,
must
FA
be,
equals
and
frac
knowing that
100,000,
VB here is
0.10.
0, VA
For object
prime
B, FB equals frac
must be VB
225,
prime
1500 equals
minus VA,
0.15 text space end.
right?
And
So
force
therefore
ratio
we
frac
have
FA,
MB
FB
VB
equal frac
prime is
0.10,
equal to
0.15
MA
equal frac 2
times
null result.
VA
Mabox
minus
frac
VB
FA,
prime
FB.
plus
Would you like a PDF version
VA.
of this explanation?
So we have VB prime times MA plus MB is equal to 2MA VA. All right, so VB prime as a result is VA times 2MA over MA plus MB. We multiply both sides divide both sides by MA, we get VA times 2 over MA over, 1, that should be 1 plus MA over MB. And so let's go all the way up here. Since MA is less than MB, the ratio MA over MB is always less than 1. So the denominator is less than 2. Therefore, VB prime will be less than 2VA over 2. In other words, VB prime will be less than, or VB prime will be greater than, I should say, VA, because it's greater than 2VA over 2, since the over 2 part, the denominator is less than 2. Okay. So for part B, we use a similar. So when C is so when A is incident on C, we have the same thing as before. We have VC prime is 2 times MA VA over MA plus MC. In the case that VC CMC is incident on MB, we have again the same idea. VC we have VB prime is equal to 2 MC VC prime two MC VC prime, that's correct, over MA over MB, I should say, plus MC. And so this is just 2MC over MB plus MC times VC prime as in here, so that's times 2MA VA over MA plus MC. All right, therefore VB prime simplifies to 4 times MA times MC times VA over MA plus MC times MB plus MC. Okay, so that's part B. In part C, we have, in part C, we want to find the maximum of, oops, didn't mean to cross that out, but in part C, we the maximum value of MC is where V prime, or is where the derivative of VB prime with respect to MC, in other words, dV prime dMC, is equal to 0. And so the derivative is actually a whole complicated expression. It's 4VA, I'm just going to write it down, 4VA MA times MA plus MC times MB plus MC minus MC times MA plus MA plus MB plus 2 MC over MA plus MC quantity squared times MB plus MC quantity squared. We set that equal to 0. And after some painstaking algebra, we'll find that MA MB minus MC squared will be 0. Therefore, MC will be square root of MA times MB. So that's part C. And finally, for part D, here is the plot. We have VB prime plotted against MC. So as we can see from the plot, the maximum VB prime is at 4.5 meters per second. And this occurs at MC equals 6 kilograms. And so we can test it out numerically. So MC from the values given here is root MA times MB, so that's 18 kilograms times 2 kilograms. This is 36, giving us 6 kilograms. So that checks out. And then VB prime max will just be we'll plug in MC, MA, and VA in there, and that will also give us 4.5 meters per second, just to check the numerical results against the graphical one. And that's it.